Thank you, Jason, for letting us to record your presentation. It's great to have you on board. I'm going to give a very quick, short introduction, briefly introduce you to the audience, which are mostly our graduate students here in the Department of Mechanical Engineering at the University of Toledo. Dr. Jason Carrol is the Global Technology Director for Eaton's Center for Materials and Manufacturing. He has his PhD in mechanical engineering from University of Michigan. And prior to working at Eaton, Dr. Carrol spends 5 years with Ria Magnet Wire. I hope I pronounced the name correctly. Ria Magnet Wire, where he served as a general manager and cooperate technical manager working for COO and CTO. This is a very, very, very brief introduction about Dr. Carrol, and he's going to give us a talk today with title Additive Manufacturing in Industrial Companies. Yeah, Carrol, again, Jason, thank you again for being with us. We have less than an hour, I would say 50 minutes for the talk, and let's have like 5 to 10 minutes for question and answer at the end of your presentation. Therefore, without further ado, stage is yours, Jason. Thank you.
Okay, so I'll give you a quick overview of Eaton, because a lot of people know Eaton, a lot of people don't. And if you do know it, growing up in Michigan, it's changed a lot in the last decade. So I'll give you a quick overview of what the company is. But my goal today is to really give you a view of where companies like ours are in additive, and you can feel it'll be kind of high level, so you feel free to ask more specific questions when we get to the end. Happy to talk about whatever I can talk about. But really kind of where we've been at, where we're going, and where is the state of additive, both from the process, quality, and design side at companies like ours, and where are we putting our investment dollars to really make additive broadly applicable within our company. And just to maybe add on to the introduction, so in my position, I work for our executive vice president and CTO, Rajamasha, and he works for our CEO, Craig. So our organization is basically working constantly with our C-level leaders across the world. Eaton's about a $20 billion company. And our job really is, in mine, I own about 3/5 of all the R&D organization in the company. And my group spans additive, advanced materials and process, and then digital design, which we'll talk a bit about that and what we're doing in that as we get into the deck. But with that, let me skip to the next slide here. Try. So Eaton has really positioned itself. If you knew Eaton from 100 years ago or even 20 years ago, and I grew up in Michigan, so that's how I knew Eaton a bit, even when I was in grad school at Michigan. It was really a company that was mostly automobile centric. And then it kind of grew at going towards the mid part of the 20th century into more of an aerospace vehicle company. And it's continued now, as it has in the later part of the 20th century, into more of an electrical company. And kind of the crescendo of that transition was a $12 billion acquisition of Cooper back about 7 years ago. And that transition is all done now, and we continue to invest in a portfolio that's centered around power management. So our whole goal, be it power for moving cars around, or the power to move airplanes, or just moving power around in general, our company is really about managing and delivering power around the world. So you'll continue to hear that theme if you learn more or listen to our investor presentations at Eaton. Like I said, we're about a $21 billion company, depending on what we're buying or unbuying at any given time. Our chairman and CEO is Craig Arnold. Craig's been our CEO for about 5 years, has spent a good chunk of time at Eaton after coming out of GE. Our headquarters, for tax reasons, is in Dublin, Ireland. Our more normal headquarters, if you will, is in Beechwood, Ohio, just south of Cleveland. That's where Craig sits. My boss is based out of Dublin, as are some of our other leaders. Our teams are spread out around the world. So from a business perspective, you see some of the headquarters here. From an R&D perspective, we're based out of Detroit, Golden, Colorado at the National Renewable Energy Labs, Milwaukee, Shanghai, and Prague are our key areas. And you can throw Dublin in as well. We have a digital AI, think AI, machine learning team that's based out of Dublin. About 90,000 to 95,000 people any given time at Eaton. So we actually presented this. I presented this slide to our investor community and our board 2 years ago, and you can see it's pretty simple. But the message we've always been trying to send, and we do this with our employees globally as often as we can, especially in this world of transitioning to data, where people are talking digital, 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 and all companies like ours are trying to repurpose themselves as kind of software companies because they, that's you get a lot more money and maybe make a lot more money quickly in that domain versus the hardware domain. But we really are a manufacturing company and have been for over the 100 years that we've been around. And so the heart of that, which is, I think, I would say my team, is how do we continue to revolutionize in that umbrella of what we call manufacturing? So what is it, and how do you really win in that space in the future? So obviously a big piece of that is additive manufacturing. My PhD was in fatigue. And so the last 20 years, I always tell people fatigue is my hobby. It's, I get to do a little bit of it with my team. We do a lot of it, to be fair, with my team in Detroit. But really, it's not about fatigue per se. Where we're really aiming is how do you design the world of voxel at a time? And to me, as you probably know, that's where additive is. We talk about atom to application and all these other, phrases around additive, but it's really about not only how do you design a voxel at a time, from an additive perspective, but how do you digitize your whole design process? And the other, and I'll talk about it in a few slides, but the other thing my team really works on and what we pitch to our leadership is the world is moving towards a place where you literally say, hey, Siri, design me a tank or design me an airplane. And our job as a company over the next, say, 10 years is to invest in how do we really become digital. And if you can imagine, we've been around for 100 years, so we have a lot of product that is designed with pencil and paper or 2D computer-aided drawing. And so how do you take that and rapidly and inexpensively turn that into a kind of a 3D digital representation of the product, such that you can then leverage that to take advantage of all the cool things that are coming around, like kind of atomic-based design, if you want to call it that, or voxel-based design and additive manufacturing. So, we gave this exact slide to our board and to our investor community because we want to show them that our investments in R&D are really focused in these areas, because we believe that additive, as most people do, is going to be the revolution that's going to take us deep into the 21st century at companies like ours. So, why is that important? Obviously, cost is always number one with our company. People want it for cheaper. Sustainability, you can't stress that enough in the world today, where companies like ours are really positioning ourselves to be leaders in sustainability. So carbon free plants, low carbon, high reusable part designs, and that's really become a big deal, especially in the investment community, that companies like ours are positioned to become quantitatively more sustainable in the near future. The other cool thing about additive, and again, the slides I'll talk about in design, is the person who, I always tell anybody can buy an additive machine. You can go spend $1 million, buy an additive machine. I could do it, put it in my garage, and compete with everybody else. So what makes you unique is always the place that the street wants to hear. And then how does what make you unique grow your business? And so for us, additive and kind of that voxel-based design methodology or mindset is where we can achieve significant system-based differentiation and win in these really emerging areas like electric vehicle and bidirectional energy systems. I'll talk a bit again in a slide, but the big piece of additive that you may know that's so difficult is we're stuck in this world of monolithic material qualification that goes back to like the beginning of humankind, where we have to make a chunk of something and then do fatigue testing, tensile testing. If you're going to a world where monolithic materials don't exist anymore, and I just gave a talk to the undergraduates at the University of Michigan a couple weeks ago, and I talked about the fact that, in a couple of generations, my great grandkids will wonder what I'm talking about when I ask them, what's it made out of? Because the idea of saying steel or aluminum or polymer or whatever isn't going to be relevant anymore, because we're going to be designing, at the kind of the voxel micron level and then producing at that level to give us unique macro properties. And so the idea of testing what is kind of a built up system where
I guess we lost his connection. Let's wait for a minute.
So, quickly, this is a high level of the journey we've been on. We started our significant additive investment towards the middle of 2016. Prior to that, we had done work like every company does and using additive for making low-cost, high-speed tooling within your operations environments throughout the world. So we continue to do that today. But starting in 2016, we heavily invested in especially powder bed, so laser powder bed. We have an EOS system and concept laser from GE. And a significant amount of money just developing those processes to be production capable. We built a plant under my organization in Detroit that we can make aerospace parts. And we did all that investment just to get the initial aerospace parts out, to get the folks like Airbus and others to accept our additive parts and starting to put them on the airframes, which is something we've done. And now we're kind of moving into the higher levels of additive maturity. So one of the big advantages of additive that people don't talk about is that you can take a part system that maybe has 50 or 100 parts on an aircraft and make it in one. And so we're additive from a process standpoint. If you say part to part, if you go from the same casting to the same additive part, you can't compete from a cost perspective. And so that makes the emergence of additive less, or the breadth of penetration of additive less, especially for powder bed. But what companies that really figure this out, they learn how to design at the system level, not the part level, and start to take quantity of parts out, as well as weight and other things. And then even the additive systems that are today, the mature, like powder bed, that are too slow and too expensive, now become, economically viable at a higher level than the part. So that's something we've taken a lot of, and we're actually winning significant new business, especially in our aerospace domain, on new platforms for aerospace primes, be it defense or domestic or commercial air travel, by designing stuff that can only be made by additive, and where we're taking what would typically be 100 or 200 parts and doing it in one or two, while being able to create package sizes and weight savings that you could never get to any conventional process that exists. So to me, that's a really where additive is going to start to hit its sweet spot. And then we'll talk about in a bit what we mean by uniquely AM, which is really how do we do crazy stuff like that voxel by voxel type of work that we're describing. A lot of our work is co-funded, if you will, or we have a lot of programs with the U.S. military as well as DOE, but a significant portion of our investment comes from the military, and they obviously have similar issues to Eaton that they're trying to deal with, from part obsolescence to just using additive in general to all the other things you could imagine. So they're a very good partner for us, and finding cool solutions that both are useful to them and useful to our customers. So again, we started in 2016 with about 3 people and a lab in Southfield. That's grown now to have an AS9100 approved quality system that is making production parts for the aerospace primes right now. We're about 20 people in Southfield and another 10 in Pune, India, where we also have additive equipment, and we're able to do global qualification and additive product development for our entirety of our company through our team in Pune and our team in Detroit. Really, our focus has been and continues to be in 4 key areas. But now I'll talk about soon, the powder bed I talked about. So we've done a lot of work in multi-scale modeling capabilities to help us design rapidly ahead of time and digitally our products before we print them. So that's a big key to how we go faster and how we qualify parts faster on the powder bed metal systems. We have, I always say I'd say the world's best nanocomposites polymer organization, in that we're able to develop our own niche polymers that have unique properties like high strength and high conductivity, be it thermal or electrical, or multitude therein. And we've learned how to print those materials and make products that nobody else can make with very unique material properties. And we're able to make a lot of our focus has been on the environmental control system. So if you're on an airplane 10 years from now flying across the Atlantic Ocean, your what is typically made out of aluminum or other metals today that takes all the air through your cabin, those will be hopefully Eaton plastic parts. And so as we progress to literally an all non-metal aircraft, those are some of the pieces that are left that aren't made out of polymers that this technology and additive help us go after it and really grow. The other area that we're into is printed electronics. So again, when you talk about product differentiation, the argument for me is additive isn't just you make a part with one machine. If you're truly thinking architecturally as a design engineer or mechanical engineer, it's about how do I take the multiple modalities that exist in additive and bring it together to create a really differentiated product. And so if you can print the electronics onto the printed part, or in the printed part, and that could be for low power, even high power applications. That's very interesting in terms of how do you package, say, like a inverter for a car, for an EV car. And so we're doing a tremendous amount of work. How do we do that in both 2 dimensions and 3 dimensions? And then how do we get from lower power applications like what we would have for LEDs, which is the picture you see on the bottom there, that actually is an printed aluminum housing that has cooling, and we've actually printed on the low power device and picked and placed on the LEDs. So that if I hit that button on the bottom, it would show you that the light comes on. So that's kind of the basic stuff that we're doing. We're also doing much more advanced things in print electronics in that area. Finally, what we've been working on since 2018 is cold spray, as you may have heard of. So into the solid state additive processes now. This was primarily because the Air Force has been pushing us to reduce our lead times for repair. Typically, when you land, say, like an F-15 and there's a problem with, say, a fuel boost pump, they pull it off, they send it back, and they wait, weeks or months to get a part that's fixed. And in many cases, because these airframes, like the B-52, the airframe is going to be 100 years soon, and so a lot of the parts that they don't stock don't have, and so there's a huge push in the U.S. military and even in the commercial aircraft world to come up with additive-based repair processes, and definitely do it in the solid state, because then you don't have to worry about heat-affected zones and deformation due to welding and things like that. So that's an area we've actually won our first commercial award just early this year with the U.S. Air Force using cold spray as a repair process. And so where are we going? Again, this slide's pretty Spartan, but it's all about, hey Siri, design me something. And we're investing a significant amount of money, and this is where I'm actually growing a global team right now around this future of how do you create engineering information management where everything in your company that you've ever designed or designing going forward is digitally understood, and all the metadata is properly structured, so that you can basically build a data layer and now broadly automate your engineering processes. So that's the speech that I give to our executives, because that means I can say I'm saving hundreds of millions of dollars. But the game we're really playing at beyond that is, again, how do I always tell people it's like an n-dimensional reduced order model is what we're going after. So how do I take a system like an aircraft and reduce it into a digital twin, if you want to call it that, and from that come up with a way to optimize the system, be it by the voxel level all the way up to the macro level of the aircraft, to meet its performance requirements, but do it in very unique ways. And so the question we've always had is how do you create a digital system that allows you to do that, as well as a company that's able to leverage that because they have their data digitally capable and digitally present. Part of this discussion, to maybe go back a bit, was, and to take it back to fatigue, is we've done a lot of work again in short crack growth. And to me, I told Ali Fatimi when he was at Toledo, and I make fun of my Wayne Jones and John Allison at Michigan, that there's no such thing as crack initiation. And it's really, crack initiation, as we've always called it, is really just short crack growth. And we call it initiation because back years ago we couldn't see crack growth at those length scales. And so with techniques like ultrasonic fatigue, you're able to watch cracks grow at 10 to the minus 12 meters per cycle. So you're literally looking at subatomic. Now again, it's not subatomic, but it's you're able to see ridiculously small increments of deformation that you can't see with traditional testing, like your 20-40 hertz type load frames. And so as we study that and continue to study that, both in simple applications as well as in bulk, where we're trying to do in situ X-ray and looking at how do 1,000 different defects or porosities, how do cracks grow from them, and do they do they obey what, the Murakami laws of, basically fatigue strength is just hardness divided by the biggest, defect or biggest hole in your structure. And so in doing all that work, what we've talked about, again, what was the kind of the beginning point of this discussion around Hey Siri was, if you could really understand the probabilistic space of short crack growth, which to me nobody has, could you design a structure that can never fail? And if you could do that, what mathematical construct would you have to try to solve that problem? Because it's like an n-dimensional probability problem at the micron level that would then tell your additive machine how to print that unbreakable material. So from that discussion has come, this whole idea of, again, how do I solve that n-dimensional reduced order model for a system, which you could be like the size of a car or an airplane, but how do I do that all the way down to the micron level, where if I could come up with science that would tell me that I can make crackless materials, then what do I need in a digital system to, in the end, tell my additive machines how to make these parts such that at the end I have the most optimal aircraft or tank or car or whatever that can be possibly derived in the planet Earth. So that's really where this team is going, and the investments that we're putting in. You can imagine that it's almost silly if you think about it. It's an extremely complex problem, but that's what we want to continue to move towards as a company. While doing that, find ways to do engineering faster through automated processes, such that we can save hundreds of millions and then reinvest that in creating these sorts of digital systems where we can create crazily cool products that differentiate us for a generation or more in the different areas that we serve. So how do we get there? To me, it's all about machine speed. So if you go to AMUG or Rapid, these kind of user and OEMs conferences for additive manufacturing, it kind of blows you away. Everybody seems to have their own additive machine, be it plastics or metal, and everyone thinks they have the right answer. But when you zoom out to the level that I'm playing at Eaton, it's all about speed. So it's all about not speed in meters per second, but speed is in kilograms per second or kilograms per hour, that you can credibly make high density metal products or high density polymeric products. And right now, you're seeing a disruption, at least I hope you are, and we're invested in the disruption around machine speed as we see, powder bed systems with lasers are really unable to scale to get to the speed that we need to make them economically viable. And you see now with like desktop metal and X1, a tremendous amount of VC money going to jet to be that differentiator in terms of speed for additive. And then the other piece, back to the computational story I just told you, is with all that being said, how do we actually invest in computers that will get us where we want to go? And you can imagine trying to solve higher order reduced order model, even on the military's biggest supercomputer, which we play around with, is not fast enough to give you that answer today. So if you're trying to create fatigueless materials, we're very interested in quantum computing and where people like Honeywell and IBM are going with that, and how do we develop algorithms that can run these sorts of computational problems in a quantum computing space versus the supercomputing space that we all use today. So again, if you're really into additive, powder bed right now is the solution that is most mature and capable, but as I said, it's too slow, expensive. The real leaders are EOS, Concept Laser. We have both of those machines, and we're just in the process of buying a 12 SLM, which is the biggest bed system on the market today, and it's the cheapest in terms of having 12 lasers in a big build box. So it's about, we always say it's about 8x more expensive with a dual laser or EOS today, which is what we traditionally have had. It's about 4x more expensive casting to go to a 4 laser system, which we've installed, and now it goes to about 2, maybe 3x of casting if you go to a 12 laser. The problem with these systems is you start putting in more lasers, you get into gas dynamic issues of how do you put the powder down, how do you control when the laser hits the powder, and how are you kind of us, Desktop Metal, HP and X1 probably have the most experience. HP more on the polymer side. Desktop Metal came out of MIT, as you may know. A lot of money is flowing to that company. They've gone public, and they're buying up everybody who's anybody in the binder jet startup space. X1's and they haven't produced a production piece of equipment for metal binder jetting yet for industrial customers, but they're about to do that. And then X1 has been making binder jet machines for over 20 years. Their focus has been mostly on making cores and molds for casting, and we've used their machines for that in the last 5 years at Eaton. But now they're really pivoting into metals, and we're actually bringing one of their machines on board in the next couple of months. And they've had a lot of focus too on aluminum and titanium, because the only drawback right now with binder jetting is to be able to have non-reactive systems where you can print aluminum and titanium and other materials that want to oxidize as you're putting them down. So that Ford is a big partner with X1, and we're very close with Ford, and they put a lot of investment on the non-ferrous side, aluminum titanium side with X1, as well as they have a fairly large equity stake with Desktop Metal. So if you have to ask me, we actually just presented this to our CEO, X1 and Desktop Metal are where we're aiming and where we're putting our investment. And Desktop just announced about 2 months ago that they're buying X1. So that deal will close in November, and we'll see how that plays out. But those are really the two major players in this area. Where we think we will be spending a lot of our time is if you look at the quality of the parts that come off these machines today, they're typically at best comparable to metal injection mold, so about 95% dense, which is about a gear for automotive or a aero, that's not going to cut it. It's not going to work. So our job is to really get that porosity level down to nothing, both in steels, aluminums, and titaniums. And obviously that has a lot to do with the binder. It has a lot to do with the curing of the binder, and then the debind and sinter step. So a lot more complexity in binder jet of how to deal with porosity, deal with shrinkage, all those things that you don't have in powder bed. So, we're very optimistic based on what we've seen and been able to do. But binder jet, there's a lot of research that needs to be done to really get these systems and different materials qualified on them, where you have strong capability and methodologies to take this to production, from the printing, the binding, the debind, and the sinter steps. So again, I kind of touched on this earlier. Our digital design, beyond creating that Hay series, n-dimensional ROM capability. Again, fatigue is my hobby, so we're always looking at and working with folks like DARPA and whatnot to try to fund how do we go after bulk short crack growth data. Because if it can be done before I retire, I'd like to make something that can't fatigue or has very strongly retarded short crack growth capability in, say, like a traditional steel or other metal alloy. And so you're really looking at, again, we get bulk short crack data that will tell us is the dislocation models and stuff like that actually, when you get beyond a grain or two in describing how cracks really grow, or is there really a probabilistic space that we have to understand and mathematically map in order for us to understand when a crack is growing in 3 dimensions at, say, a micron, what does it see in front of it versus as a function of energy states, and which path does it choose and why? And so that's an area where there's almost no data other than people like Mike Sanjeev and others who work at Argonne to go and look at multi-grain high X-ray energy systems to look at how do different dislocations actually move through multiple grains, and how does a crack really go? There's just a paucity of data there. So our team is really trying to figure that out. How do we get bulk short crack data? And again, that all plays into computational material science, ICME, mesoscale physics, which to me is kind of the undiscovered country of materials, where between the quantum level and the micro level, what is going on. And then finally, the data science things of, can we approach these problems through data science, kind of top down versus first principles up, and try to meet in the middle and find new ways to characterize crack growth and things like that that we don't use today. So again, that gets into our idea of voxel-based design for additive. So again, we combine traditional thermal solidification models with crystal plasticity, with high energy, high resolution characterization in the bulk, and then things like homogenization theory that allows us to plug this module into our digital system and start creating ways to create emergent material properties that you can't do through traditional processing routes. So I probably went through this pretty quick, so we'll have a bit more time for questions, and I'm happy to answer anything you may have in terms of depth or questions around this, and specifically what we're doing at Eaton. But again, for us, it's all about machine speed and digital design for AM. And so for companies like us to win, you have to have an AM process that can scale, that's fast, and is better than or as good as or cheaper than traditional processing. And I would tell you, I think the world's that's right around the corner for the world. So in the next couple of years, I really think that's going to happen. And a lot of what we've talked about with additive being disruptive to traditional manufacturing and extended value streams like we have today and we're suffering from because of COVID, a lot of that's going to go away very rapidly. So where we went from a BlackBerry to an Apple phone, I think you're going to see a lot of that transformation now starting to happen in the next few years with binder jet and other high-speed machines. And then again, for companies to really take advantage of that, you have to change your whole engineering process and people to think additive design, not just at the part level, but at the architecture system level. And so that's a struggle for companies like Eaton of how do we educate our people and give them the right tools they need to do that digital design correctly. And my argument, as I think I was making before, is that I believe that the complexity of design for additive is beyond any one person or group of people. Where today we design and we do like a CAD model, we do a finite element stress model, a CFD model, and that's multiple people kind of in series tied together trying to come up with an optimal design. To do that with the complexity that we're talking about with kind of higher level architectures for additive, voxel-based design, things like topology and generative design algorithms, trying to do that with a person or a group of people is extremely difficult, especially because a lot of those require people with PhDs to really get the most value out of them. So again, there's the reason we're so excited about investing in digital design is we're trying to create where the computer does 90% of the work even now, so that the one human who's generically capable of mechanical design can create some really cool stuff. So again, I think that's a key piece to really seeing additive take off in the world. And then the thing that holds us back, and I touched on it before, nothing makes me more angry and more passionate about materials is when you're still characterizing stuff like it's 1950. And I don't care if it's Lockheed or Boeing or GM or Ford, everybody still thinks I have to do SN curves and I have to do tensile tests and all this nonsense that we convinced ourselves was the right answer in the world of big chunks of steel or aluminum, and we just want to get a general understanding of the bulk properties of something. That doesn't work in additive, because every time you change a power or velocity in your design, you have basically a different material response. And so you'd have to go recharacterize that. And as we all know, doing fatigue testing traditionally with slow 40 hertz, 20 hertz processes, you spend millions of dollars and take forever to get what you need to go into production. So we really need a revolution in how we characterize our materials, which is why for my entire life I talked about ultrasonic fatigue. And we have that equipment in Southfield as well as we use all the equipment at Michigan, Santa Barbara, and our colleague Harry Meyer in Vienna to really bring that technique to become the ASTM approved technique for additive. I think that's very critical that we do that, as well as find other ways to characterize these more complex material systems that we're developing for additive manufacturing. And if you haven't caught on, my team used to be a materials team. Now I'm hiring mathematicians and digital people because the person who's good at steel physical metallurgy is just as important to me as the person who can create APIs to string software systems together and help us create that digital system. So it's a very multidisciplinary world out there today. And, I'd love to see how universities change to help create these more hybrid employees for us that can play in the different aspects of disciplines that are needed to really make additive take off in companies like ours. So with that, feel free to ask any questions. Happy to answer anything you have.
Sure. Thank you so very much, Jason, for such a great talk. I really learned a lot. But we met before, and I told you that yes, we have a gigacycle ultrasonic fatigue system in the fatigue lab at University of Toledo, and I personally have 2 PhD students working on fatigue of additively manufactured metals. So we are open to collaboration, as we have talked before. Karim, I do not have access to the questions. I guess here you need to help me a bit. I cannot see the questions. If there are some questions, please feel free to ask. I have one particular question that I can ask at the end. Go ahead, Karim.
So Karim, can you read the
Karim or
questions in
Hussein,
the
one
chat
of
box?
you.
Yes, yes.
Oh, okay. Yeah, I see the questions are not in Q&A, they're in the chat box.
In the chat, yes.
Okay, good.
So we have a question from Hussein Abedi, and he said that you told that 2019 your industrial sales is $8 billion. Would you explain if that is a big number or not? And which kind of parts are you printing more with additive manufacturing, particularly for automotive?
Yeah, so I mean, I don't know the context of the question, but 8 billion is pretty typical of our industrial sector. We're split up into 2 sectors. About 13 million is characterized as electrical. The 8 billion is industrial, which is really our aircraft, our aerospace and industrial vehicle group businesses, which includes our e-mobility business, which is focused on EV platforms for transportation. Definitely want to see that number grow. So it's not big enough. Would be what our CEO would say. We'd love to add a couple billion to that in the next year or two in terms of organic growth. We're printing right now. Our what we're making for production is all in aerospace, and almost all of it is in aluminum silicon mag right now. That's where we focus, and that's where a lot of the aviation world's focused, other than in niche areas where titanium is particularly useful. And we're also printing in titanium because we're moving towards products that see high stress on the airframe and that you don't want to have fail on you, because it tends to make your engine stop and things like that, which you don't want to have happen. So the whole industry is matured to the point where now we can take on and quote additive parts that are significantly stressed and very much part of the the reliability of the system. So that's where we're pivoting. Automotive, nobody's really there yet, including us. So we're with binder jet emerging. There's a lot of plays, I think, in automotive. And that's why you see people like Ford so invested and Desktop Metal and X1. And Eaton's moving in that direction, not just because of automotive, but because our electrical sector, majority of what we make there just sits in a box. So as long as you can put a screw into it and put a powder coated metal frame to it, you're good. So if you can make that cheaper, better, quicker, without inventory and tooling, with additive, you win. And so that's where binder jet to us is really the scaling play for Eaton, and it's across multiple materials, be it steel, aluminum, titanium, or anything else that we can figure out how to print and sinter with binder jet.
Yeah, thank you, Jason. And he has a following question: how it's possible to increase the speed of AM or additive manufacturing?
In the powder bed space, it's easy. You just put porosity where you don't care. And this is the big argument that gets you to ultrasonic fatigue and away from ASTM standards of how we think about materials. Is one of the things we've done early on was if you do an FEA of a piece of metal and you have a stress distribution where some places have high stress, the rest of it has low. As a fatigue person, my response is where you have no stress, put no material, because you don't care. So as long as you can keep the kind of the global stiffness of your product within range of what you need, you don't want this thing moving around when it shouldn't be. You have porosity, and from my perspective, I know how to map porosity. I know how to convert from extreme value distribution of porosity to fatigue strength very, very accurately. So with that being said, one of the things we do is you can make the layer thicknesses bigger. That's an easy thing, but you can also tell the machine to go as fast as it can, which means you don't have enough energy density, so you get lack of fusion porosity. But if you know as a function of your P and your V, your process or your laser power and your
Did we lose our speaker, Karim? Yes.
I guess we lost the signal for a second.
Yeah, maybe wait because it happened once
Sure.
before. I
Yeah,
guess.
a couple of times. Yeah.
Didn't see
So
the
angry
slide.
and passionate is what's holding additive back is that mindset of, we used to think if I make something, I cast it, and then I go look at it with non-destructive testing. It doesn't have any things in it that are bigger than what my fatigue or fracture mechanics people told me were acceptable. To me, that's a very 20th century way of looking at materials. And we have to accept that, with in situ monitoring and AM and things like that, the world is not far away from being able to give you all the kind of the DNA of your product and allow people like me to put in porosity and things like that where it doesn't matter, and not have to look for it later. I can just look and say, I'm allowing this in this voxel. I want this extreme value distribution. Did I get it or not? And if I didn't, I'll have the laser go back over and get it to where I want it to go. But all of that allows us to increase speed. But again, it's slowed down by an industry that's living in the middle part of the last century.
Thank you. Another question from Bilal. Can you elaborate more on the machine learning aspect of Eaton? Are they algorithm physics driven?
A bit of both. I'm not a big fan of physics because if I can get the same solution through a regression model, I'm good. So it's a bit of both. Obviously, I'd say more on the non-physics side, which is why machine learning and how do you parse, n-dimensional data spaces becomes very interesting to us, because if I can learn the answer through math but not have any idea what's actually going on, do I care? And that's so, yeah, I'd say a bit of both, but definitely we lean towards if the computer can figure it out, I don't need to know how. And if it can do that in multiple different aspects and different designs, then we're happy. And are there openings? There are maybe a couple right now. There'll be a lot more going into the new year.
Yeah, and the second part of his question is, are there any current openings at Eaton? I believe in the same field of maybe machine learning, additive manufacturing.
Yes, we're definitely building our team there. I think there's a couple open now, but a lot more coming as we go into the new year.
Thank you very much. Perhaps whenever such opportunities open up, if you can share it with us, our grad students definitely appreciate it.
Yeah, no problem. Happy to do it.
Thank you.
Dr. Borganji, I think you're unmuted if you have a question.
Sure, thank you. Thanks, Jason, for the presentation and giving us the perspective of what you guys are doing at Eaton. I'm wondering, when you are putting emphasis on digitalization and you're talking about getting into digital design, where this design starts for you guys and where it finishes in the entire value chain of additive manufacturing.
It should start at the beginning of any design, that we look at additive and how do we really attack that system level problem. I would tell you we're not there yet. We're more of, hey, we have a current product where that we're trying to redesign with additive. Maybe the best place that it's going today is looking at new products that are kind of offshoots of existing products in our aerospace business. And the reason why we're not there yet is, again, back to how do you educate your design. We have about 2,500 design engineers globally. How do we educate them and give them the tools to really look at additive from a system level down, and then apply things like generative design and topology optimization and make sure those digital systems are there? We're just not there yet. So hopefully in a year I could come back and say it really begins at the requirements level, and hopefully, as a lot of our customers are becoming more savvy, you're getting requests for quote that are impossible to meet with traditional processing. And so, that's very exciting for us, because then our capabilities in additive become very, useful. But again, it's only a select group of engineers that we have at Eaton right now who know what I'm talking about and know how to get access to the tools to really create something that's very unique and meets those requirements. So I see that being a place that we're going to continue to grow, so that, again, my answer will be the requirements come in and you realize either you can't make it with traditional, or you could get a lot better value through additive. And it's basically having that capability to do that decision tree quickly is really going to be effective for making additive more broad spread in our company.
Sure. Yeah, I think that's really interesting what you're saying, but just wanted to give a little bit more color into this. And since I'm a materials engineer, I'm a metallurgist. When I'm talking about digital design, I'm not only looking at the CAD and how it gets to the STO, and you just make a build prep. You know, to me, digital design starts with material design and how we can start digitalizing our material design, digitalizing our powder, digitalizing our post processes. And I think this is that something you know, a big company like Eaton, with having access to a different portion of this value chain, can actually contribute. And if you guys look at design, not only and digitalization, not only from the perspective of the CAD file design, which is important, but the entire value chain, I think that really increased this kind of, okay, we need to have a different thinking. And certainly university and us, we can contribute to that.
No, I agree. Maybe my quick response would be, yeah, I 100% agree. And then you think of, you know, how do you translate that into something designers or computers can use? And it's, to me, it's kind of like you have transfer functions from, you know, you believe that, like, again, Murakami's equation for fatigue. It's great that it's a machine learned model, if you will. It's a regression model that's very, very accurate. All I need is the Vickers harness and a distribution of defects model, and I win. So it's accepting that, and then how do I relate that back to the PV space of a laser system and go map that quickly, which we know how to do. You know, we can do that in an hour with a sample we make that has every PV combination, and then we go CT scan it and back out all the extreme value distributions and hardnesses, and we can do that, you know, 100 times for very little money, very quickly, and have a good statistical understanding of what this machine can do. And then, you know, if you can link that to, if I did, you know, how many voxels that differently can actually put next to each other and get those unique benefits before stuff starts to blend and all that stuff. You know, I think having that is critical. And I make fun of ANSYS. We work with ANSYS a lot, and their CEO and CTO. It's like, you know, we're buying Granta today, which you may be familiar with, and it's, you know, it's a database of monolithic materials. And you're going, what do you do, guys? I'm paying how much? I don't care. That world's kind of dying. So it's, I always tell ANSYS, yeah, it'd be more valuable to me, and I know their CEO sees this too, is if you could help me with what I just talked about. And then, yeah, maybe you know, again, the material is no longer, the material doesn't mean anything from a monolithic perspective. And so how do we store that by storing the process parameters that give us certain material outcomes, you know, voxel by voxel or layer by layer. And that becomes an input to our digital design process. And again, but that only works if the community of, you know, the primes like Lockheed, Boeing, and folks like that, you know, accept that, hey, Jason's going to put porosity, a big hole in my, you know, I tell our CEO, if you had a crankshaft and you would pull it out of your car and it had a huge hole through it, would you care? You wouldn't, because you never look. As long as it works, you don't care. So if I can do that, why does anybody care? It's just because we live in this world of, you know, fatigue tolerant design and all the stuff that came out of, you know, Paul Paris and the work in the 60s that we're still kind of infatuated with. And we just have to get out of this monolithic mindset.
I agree 100%. I like the fact that you actually bring fatigue in every discussion and look at from that angle. Yep.
Well, you got to realize I catch all the things that go wrong at the company too. And, you know, when people try to ask you, why did this fail? You kind of laugh because, you know, companies like ours have lost a lot of that knowledge. And so the few people you have left to even know how to spell fatigue are literally living in the 1950s, because that's the last time they learned. You know, I make fun of Wayne Jones at Michigan. Like, what are you teaching these kids? Because if it's about, you know, Paul Paris, I knew Paul Paris, but it's kind of outdated. How do we think differently? And even Murakami was 1990s when this stuff was invented. It's not recent. And, you know, our CEO says, well, ultrasonic's new, nobody accepts it. I go, ultrasonic fatigue testing was made at Bell Labs in the 1950s. You know, the first international conference on it was in 1980. You know, guys, come on, that's like half a century ago. We're not contemporary. So we have to, and I have these talks with, you know, the leaders of Lockheed and anybody, is as a community, we have to, if we're going to be successful as, you know, the United States or the companies that, you know, that drive themselves from here, we're not going to win if we keep thinking like this. Somebody in China or Elon Musk is going to decide that he can live with this and know how to do it and go take our business from us because he's not stuck in the 1950s.
Agree. Thanks, Jason.
Karim, can I ask a quick question?
Mhm.
Yes, sure.
Jason, I have a question here back to this ultrasonic fatigue. Let's assume we print a part with optimal print parameters. Then we do perfect polishing and even we run HIP. And let's ideally assume this part is defect-free. There is no internal defect like lack of fusion or so forth. Then if we run ultrasonic fatigue, most probably crack initiates from somewhere on the surface. Therefore, what would be really the difference between ultrasonic fatigue in this hypothetical scenario and, let's say, a conventionally fabricated rod part?
I don't think any. I mean, that comes back to what are our models for surface. And again, I hate to say initiation, but those kind of questions are where my hypothesis of no such thing as initiation runs out. Right? There is in a perfectly pure titanium material, which I always make fun of the Air Force guys of like you're the only people who can afford that kind of stuff. The rest of us have to live with the fact that we have cracks and holes and stuff already in our materials. But yeah, in the end of the day, the surface is going to win then, and you just have to again back to the transfer functions of the different parameters that define surface like roughness parameters and things like that. And how does that relate back to kind of Murakami's equation or something like it so that you can parameterize that in a 2 to 3 dimensional perspective and link it back to fatigue. So then you're designing the surface from an additive perspective to be a certain way to keep your fatigue where you want it, your life of your product to be where you want it to be. But I think it's a good question. In the end of the day, I don't think we know a lot about how cracks actually form at surfaces. We talk about stress concentrations back to like John Barsoom in the 1960s and stuff. Good stuff, but not physically relevant. So I'd definitely be interested too of again back to short crack growth initiation at the surface and what does that look like in additively manufactured parts?
Gotcha. Thank you.
Mhm.
Karim, is there any other question for our
Yes.
have a
From Andrew
question.
Bromley. He says, as a former F-15 crew chief, I can greatly appreciate this technology. A lot of man hours and flight hours are wasted due to the lack of parts. His question is, if the intentions for these machines to allow the parts to be manufactured in the field, if that's the case, are there ways to ensure the quality and reliability of parts printed to ensure flight safety?
Yeah, so we're actually working on a couple of programs with the Air Force, and our goal really at a high level is you're going to take a box on wheels, wheel it up to your F-15, take your fuel manifold off, throw it onto the conveyor belt. It's going to go through 3D scan it, inside and out. It could be 3D and X-ray, and parameterize that, bump it up against what the overhaul limits of that device is, and say can it be fixed or not. If it needs to be fixed, then goes to a number of different paths on that machine. It could be cold spray, it could be friction stir welded additive manufacturing or whatever, and goes and executes that and then does the finished machining on it. To me, that's able to be done. We actually have a lot of those parts already put together to apply to the work that we're doing with the Air Force. It is still an issue, though. Again, in situ and inspection in powder bed is not mature, but pretty good. I mean, I can tell if I have a decent sized defect post build or even now on the new systems with each layer. That doesn't exist yet for say cold spray. So that's something we're working on. We can definitely do the post quality control inspection with advanced NDT methods, but we'd prefer not to do that because we'd want to be able to see smaller defects and understand how they may affect the product. So there is some investment that we're starting to do in situ for cold spray and other non-thermal processes that we think work very well across all of these products. The other add-on to that is that we can actually make the product better than when it was put in service say a decade ago, because we can have an aluminum fuel housing or hydraulic manifold for an F-15 or whatever, and we can go add aluminum silicon carbide. We can start to grade and create unique materials that make that part better than the first time it was used. And so that's part of the the lead time is a huge thing. That's what the Air Force cares about, because they don't want their planes sitting there, obviously, and they've lost them in like hurricanes where you can't fly it out of Louisiana or Florida because you don't have the part, and then it blows away. And when the
I guess while we're waiting for our speaker to come back. Are there any last minute questions for you guys to put in the chat box Q&A, or just simply unmute yourself? Kareem, can you hear us? Okay.
Jason,
Hello.
we lost your signal for
Oh,
I would
sorry.
say 10-15 seconds. If you said anything within last 10-15 seconds, please repeat it.
Oh, I don't know where I left off, but maybe I said it all.
Okay. Karim, is there any other question in the chat box for the audience?
Nope.
Okay.
We're done with the questions from the chat box.
Okay, Dr. Sujudi, would you like to close this session? On my end, Jason, again, thank you so very much for being with us today. Such a great talk. And if there is anything else you want to add?
No, thank
Said,
you. And thank you, Jason, for this interactive presentation. Really appreciate your time, and hopefully we'll be in touch. And our students are definitely eager to hear more about the opportunities at Eaton, learn more.
Wonderful. Well, thank you so much.
Thank you.
Thank you, everyone. Thank you, and have a great weekend.
Take care.
Thanks.
Hello?